In this lecture, we will understand what do we mean by sampling and what is sampling theorem. Till now, we have done a lot of discussions on continuous time signals, and now it's time to move on to discrete time signals. But wait, why we are required to study the concepts related to discrete time signals when we already have continuous time signals? The answer is extensive use of digital technologies nowadays. So if you look around yourself, you will find there are so many digital technologies in implementation, but we know all real life signals are analog in nature, or you can say all real life signals are continuous in nature, so they are continuous time signals. So the information is carried by continuous time signal, but the systems we are using are digital in nature. Therefore, they will not process continuous time signal, and it becomes important to convert the continuous time signal to discrete time signal. And this process of conversion, or you can say reduction of continuous time signal to discrete time signal, is known as sampling. Now let us define sampling properly. Sampling is the process of reduction of a continuous time signal to a discrete time signal. And if you want to get the continuous time signal back from the discrete time signal, then you can do this, but there is some condition. And now we will try to obtain that particular condition. So let's move on to the next part of this lecture. Let us take one continuous time signal, and let's say we want to convert this continuous time signal to a discrete time signal, and we are representing this continuous time signal by mt, and we are representing it by mt because this signal is known as message signal. This is known as message signal because this signal is carrying the information we want to process. And you must note one point here. This signal we have taken is a band limited signal. We are assuming that we have taken a continuous time signal which is a band limited signal. Now why we are taking band limited signal and what is band limited signal, I will explain now. Band limited signal means its Fourier transform, or you can say the spectrum of this signal, will be non-zero only within a small range of frequencies. For example, let's say this signal is having the Fourier transform m omega like this. Now you can see that the Fourier transform or the spectrum is non-zero from minus omega m to plus omega m. So here in this case, we are having the spectrum which is non-zero only for a finite range of frequencies, and it will be very helpful when we will try to extract the continuous time signal from the converted discrete time signal. And this point will be more clear after some time. So for now, just understand that we are having a continuous time signal carrying the message, and its Fourier transform is like this, and the Fourier transform is non-zero between minus omega m and omega m. And also note down what is omega m. Omega m is the maximum frequency component of the message signal mt. Omega m will be used a lot in this course, so remember what it is. It is the maximum frequency component of mt. If mt is having multiple frequency components, then the maximum frequency out of those frequency components is omega m. In the next lecture, we will solve numerical problem, and there this point will be more clear. Now we will move on to the next process, and the next process is feeding this continuous time signal to a device known as sampler. Now this device, sampler, is simply acting as multiplier. it is acting as multiplier, and multiplier means it is going to multiply two continuous time signals. First signal is mt and the second signal is ct, and you can clearly see that ct is a periodic impulse train, and this periodic impulse train is having the fundamental time period equal to ts. So ts is the fundamental time period, or it is the sampling period. It is also known as sampling period. It is also known as sampling interval. It is also known as sampling interval. And we know omega s, which is the angular frequency, is equal to 2 pi divided by ts, and omega s is known as the sampling frequency. It is known as the sampling frequency. So now we have two frequencies. The first frequency is omega m, known as the maximum frequency component of mt, and the another frequency we have is omega s, which is the sampling frequency or the angular frequency of this periodic impulse train. And remember both the frequencies, because we are going to get relation between these two frequencies only. And as we are having the periodic impulse train like this, we can write it as summation n equal to minus infinity to infinity delta t minus n ts. Now when n is equal to 0, we will have delta t. This means impulse present at the origin. When n is equal to 1, we will have delta t minus ts. This means the unit impulse which is present at ts. Simply shift the unit impulse present at the origin towards the right by ts, and you will have delta t minus ts. So this impulse you are looking here is delta t minus ts. This impulse is delta t. This impulse is delta t plus ts, and we will have it when n is equal to minus 1. Similarly, we will have all the other impulses, and we will have the impulse train like this. Now, after multiplying mt and ct, we will have the resultant waveform like this. In this waveform, we are having different impulses, and the area or weight of the impulse is equal to the instantaneous value of signal mt. For example, if you talk about the impulse present at ts, then this impulse will have the weight or strength equal to the instantaneous value of mt. This means when t is equal to ts, the value of mt will be the strength or weight of this particular impulse. And in this way we have a new signal which is known as sampled signal and represented by st. st is equal to mt, message signal, multiplied to the periodic impulse train ct. And now we are interested in obtaining the spectrum of the sampled signal. This means we are having st and we want to have the Fourier transform as omega of st, and we also know that st is equal to message signal multiplied to the periodic impulse train ct. And we know the property of Fourier transform when two signals are multiplied. If you try to take the Fourier transform, then on the left hand side you will have the Fourier transform of this signal, which is s omega, and on the right hand side you will have 1 divided by 2 pi multiplied to the Fourier transform of mt, which is m omega, convoluted with the Fourier transform of ct, and let's say Fourier transform of ct is c omega. So we can easily obtain the Fourier transform s omega after convoluting m omega and c omega and then dividing it by 2 pi. M omega we have assumed here, but what about c omega? If you remember, in the Fourier transform solved problem number 11, we solved one problem in which the time domain signal was exactly like this, and we obtained the Fourier transform of this signal, and the result we got was equal to omega s summation n equal to minus infinity to infinity delta omega minus n omega s. So we have c omega and we have m omega. Now let's move on to the simplification of this. And in order to simplify this, we need to use the properties of convolution and the properties of impulse signal. We are having s omega equal to 1 over 2 pi multiplied to m omega convolution with c omega, and c omega is equal to this. So we will write omega s summation n equal to minus infinity to infinity delta omega minus n omega s. And we can take this omega s outside, then we will have s omega equal to omega s divided by 2 pi inside the bracket m omega convolution with summation n equal to minus infinity to infinity delta omega minus n omega s. And we know omega s divided by 2 pi will be equal to 1 over ts. From here you can see that omega s divided by 2 pi will be equal to 1 over ts. So in the next step, we will write omega s divided by 2 pi equal to 1 over ts, and inside the bracket we can rearrange this and we can write summation n equal to minus infinity to infinity m omega convolution with delta omega minus n omega s. And we know the property by which we can simplify this further, and according to the property, if we have a signal xt and this signal is convoluted with delta t minus t1, then this is equal to xt minus t1. We simply need to put t minus t1 in place of t, and if we follow this, we will put omega minus n omega s in place of this omega. So in the next step, we will have s omega equal to 1 divided by ts inside the bracket summation n equal to minus infinity to infinity m omega minus n omega s, m omega minus n omega s. This is what we need. And now let's expand this by putting the different values of n. So we will have s omega equal to 1 divided by ts inside the bracket. When n is equal to 0, we will have m omega, and we have the waveform of m omega. Now when n is equal to 1, we will have m omega minus omega s. So we will have m omega minus omega s. Similarly, we will have different terms. When n is equal to minus 1, we will have m omega plus omega s. We will have m omega plus omega s. Similarly, for negative values of n, we will have different terms. So in this way, we are getting the expansion of s omega, and using this expansion, we can plot the waveform of s omega, and the waveform will look like this. If you refer the expansion, you will find when n is equal to 0, we are having m omega. This means we should have this waveform, and therefore this waveform here is the waveform of m omega. This makes this frequency equal to minus omega m and this frequency equal to omega m. And when n is equal to 1, we are having m omega minus omega s. This means m omega is shifted towards the right by omega s. This makes this frequency here, this frequency equal to omega s minus omega m. This frequency here equal to omega m plus omega s, or you can write omega s plus omega m, and this particular frequency here equal to omega s. Now you can notice one thing, that omega s minus omega m is greater than omega m. Omega s minus omega m is greater than omega m. This implies we are getting omega s greater than twice of omega m. So when omega s, which is the sampling frequency, greater than twice of maximum frequency component of the message signal, then there is no overlapping in this spectrum. By no overlapping, I mean this triangle and this triangle are not overlapping. There is sufficient gap between the two triangles, and this gap here is known as guard band. Now what will happen when omega s minus omega m is equal to omega m? This means this frequency here, which is omega m, is equal to this frequency here, which is omega s minus omega m. It is very obvious that the triangles will be touching. So you will have the waveform like this when omega s minus omega m is equal to omega m, or you can say omega s is equal to twice of omega m. Now in the two scenarios we have discussed till now, we can recover the continuous time signal from the sampled signal because there is no overlapping. In the first case there is a gap and hence there is no overlapping. In the second case they are touching and again there is no overlapping. But if there is overlapping, then we cannot recover the continuous time signal accurately. Now let's try to understand in what condition the overlapping will occur. We have discussed the first case in which we found when omega s is greater than twice of omega m, there will be gap, and when omega s is equal to twice of omega m, there will be touching case, and when omega s is less than twice of omega m, when omega s is less than twice of omega m, then there will be overlapping, as you can see on your screen. And you can understand the point that omega s minus omega m is less than omega m. This makes the overlapping possible, and in this scenario you cannot recover the continuous time signal accurately, and this is known as sampling theorem. So let's move on to the final statement of sampling theorem. According to sampling theorem, a signal can be represented in its samples like we have done. We have represented signal mt in its samples, which is sampled signal st, and can be recovered back when the sampling frequency, this means omega s, is greater than or equal to twice of maximum frequency component present in the signal. This means twice of omega m. So when omega s is greater or equal to twice of omega m, we can recover back the signal from its samples. So remember this condition, omega s should be greater or equal to twice of omega m. This is very important condition. So this is all for the sampling theorem, and initially I told you that we are considering the band limited signal. We considered our message signal to be band limited signal to get the Fourier transform like this, and we are getting the Fourier transform like this because we don't want the overlapping. Now we will try to understand this point by the help of one example, and in this example we are considering the time domain signal as not band limited, and as the time domain signal is not band limited, the Fourier transform will not be bounded like this. It will be something like this. Now repeat this structure like this and you will find there is overlapping, and we are trying to avoid the overlapping so that we can recover the time domain signal from its samples. But if you take the not band limited signal, you will have the overlapping and therefore recovery will not be possible. And this is the reason we are taking the band limited signal. And this is all for this lecture. See you in the next one.